How are you? Hope everything is going all right. We're just going to finish off chapter 1 here. My name is Ian Coates, and welcome to Math 1031. We're just going to finish off section 1.3 here, and hope you're having a great day. It's a nice short little video, okay? So, moving straight on to sampling. Now, we've talked about the variable, we've talked about discrete and continuous, and we've talked about qualitative and quantitative in previous videos there. Now we're moving on into sampling, which refers to the process of selecting a sample from the population. And this is a pretty important step here because this kind of signifies what statistic is really about, right? There's not enough money in the world there to go around and ask everybody in Canada who they're going to vote for in the next election. So what we do is we take a sample of the population, and then with some degree of error, you're not going to get away from it, right? Because you're going to take this sample and project it onto the entire population, right? And there is going to be a degree of error, okay? But this comes with the business, right? So we often study samples rather than entire populations due to some of the following reasons. Reaching the entire population ain't possible. Reaching the entire population is too time-consuming, too expensive. Some studies render selected samples unusable after testing, like on auto crash testing, right? Once a vehicle has been smashed up, you can't use it again, so you got to do it again, right? So, a sample that is not properly selected, thus resulting in a poor representation, is said to be biased. There's that word again that we introduced during chapters 1.1, right? You never want bias. Bias is the where you, as the experimenter, are skewing the data in a particular direction, and you're not letting the numbers sing. You have to, right? Let the data, the numbers talk for themselves, right? Researchers strive to ensure that the elements included in a sample are selected entirely by chance. This is called random sampling, okay? Where the experimenter isn't really involved, the numbers, the participants in the sample are randomly selected. There's a whole bunch of them here. There's what we call simple random sampling, stratified random sampling, systematic random sampling, cluster sampling, multi-stage random sampling, and convenience sampling. Okay? While a true random sample can be difficult to obtain, researchers still try to include randomness in their sample selection process by adopting a sampling method or plan. Okay? So, first of them here, simple random samples are obtained from a population such that every element in the population has the same chance of being included in the sample. Several different sampling methods here, drawing numbers or names from a bin, right? All of these guys here have an equal opportunity to be selected. Okay, it's what we call simple random sampling. Assigning values to every element in the population and using a computerized random number generator to select the value. Sure. Using a random number table and a thumbtack there to select numbers corresponding to identification numbers of elements. Sure. Whatever works. Okay. Just ensuring there that when this is the population here, and if you're going to choose 3 of them, all of these guys here have the same opportunity of being selected. That's all that is. Steps to selecting a simple random sample. Assign a number from 1 to n. 10, 15, however many you have in here, right? Determine the sample size, okay, which would be small n, okay, and randomly select as many as you like for your sample. So in this case here, we're looking for a sample size of 6, right? And you just blindly choose 6 of them. Stratified random samples are obtained by first dividing the population into a subgroup, or what we call strata, then selecting simple random samples from each of the levels or subgroups, or what we call stratum. Now, why would you want to do this there? Going back into the example there we've been using, the whole idea is that there's an upcoming election in Canada, and you want to get a good idea of who is going to vote for each candidate, right? And if you only chose all of your constituents there from one neighborhood, well, people in neighborhoods tend to think alike. So you maybe you want to break it up, break the population up into provinces and territories. All right, that could be your strata, right? Researchers may want to stratify the population according to age, income, right? 0 to 35,000, 35 to 70,000, 70,000 to 150, 150 to 400. Break it all up. Health conditions, sex, nationality, right? This is a form of random sampling often used when a population is heterogeneous. That is, the population is a collection of subgroups that differ in characteristics. Now, if you were choosing there from a single classroom, well, you know what I mean, you'd want to keep it as is, but when you're dealing with population across a huge country like Canada, there are going to be subgroups all over the place, okay, based on any number, okay, of parameters. So, steps to selecting a stratified random sample: identify the particular attribute strata to be isolated, right? Stratify the population into those groups, and then you select a random number from each of those groups. So here, I've got blue dots and green dots here. I could just simple random sample, but I may not get what I'm looking for. So if you break it up into the different strata, and then now you have a true representative of what is going on. You've got 6 in your sample size. 3 are most definitely green. 3 are most definitely blue. So, and moving on there to step 3, we just looked at step 1, step 2. Okay, step 3 there, you select that random sample from each stratum. There's a proportion allocation, equal allocation, right? So the proportion allocation, the size of the strata is in the sample are proportional to the size of the strata in the population. Well, they are, right? And equal allocation, the size of the strata in the sample are all equal. You got 3 green, excuse me, and 3 blue. So everything works out fine, okay? There's systematic random samples. We use these there sometimes. They're obtained there from an ordered population by first choosing an element at a random starting value and then choosing subsequent elements at a predetermined periodic interval. Well, what does that mean? Here we've got this data, and it appears to be in some type of an order, okay, in a straight line. Whatever that order is, it could be age, it could be marks on a math test, could be whatever, right? And so in this case here, the population size there, capital N, is equal to 20. Okay. We're going to choose an interval value of k is equal to 4. And we're just going to randomly choose a starting point, the third element. Okay. So now, where this guy here is coming into our sample, and then 1, 2, 3, 4. This guy's coming in. 1, 2, 3, 4. This guy's coming in. 1, 2, 3, 4. And you see the pattern here, right? So it's what we call a systematic random sample. This approach is best used if the population is homogeneous with respect to the variable being studied, right? As we said there, marks on a math test, these kinds of things. Good. Steps to selecting a systematic random sample. Number 1, create an ordered list of all elements in the population, right? Capital N is equal to 20, and they're all kind of ranked. Whether this is high to low or low to high, it doesn't matter. Divide the population size n by the desired sample size n to get the interval k. So if you're looking for 5 people to come out of this population of 20, 20 divided by 5 is 4. That's where they get that k value is equal to 4. Okay? Randomly select a starting point there between 1 and k. So in this case here, 1 and 4. So you would randomly choose 1, 2, 3, or 4. And wherever you chose from, that is where you would start. Okay, in this case here, the example started at 3, which does fall between 1 and 4. And then choose the element corresponding to every 4th value from your starting value. Okay? Cluster samples are obtained by first dividing the population into several clusters or groups, then randomly selecting some clusters and sampling every element in the selected cluster. So in order to get a sense of patient satisfaction with the level of care in a regional hospital, a few wards from the hospital may be randomly selected. Again, in order to get a sense of patient satisfaction within the level of care of a particular hospital, a few of the wards, right? You've got pediatrics, maybe you've got oncology, you've got emerge, okay? So, if you just randomly chose people, you may not even get somebody there who is from emergency, right? You want to know how all of the aspects of the hospital are doing. So, right? So all the different departments there of the hospital. Okay, we break it up into clusters or groups, right? And, okay, and we'll show you this right here. So steps to doing a cluster sampling: divide the population into the clusters there that you want, the different groups. Randomly select some of the clusters, okay? And that's what you do. You grab this one and this one. All the elements in the selected cluster become the sample. What we call cluster sampling. Okay? Multi-stage random sampling. You can kind of see what's going on here. We have all these different dots in the population, and then we stratify them, right? Just like we did before. Where was that one? Right here, right? In this case here, we had blue and green, and we stratified them, right? And then chose. No, I'll never be able to find this again. Right there. So we stratify these here, and then it appears there that we create clusters, as we did in the previous example, right? Cluster sampling. Okay, so this is what we call multi-stage random sampling. These are obtained from a large population by using one or more of the aforementioned sampling methods in a sequence. So in order to determine the public's rating of government, first regions, then communities and neighborhoods are selected according to a stratified sample. Finally, specific clusters are then selected from there. So you stratify this, right? And then you cluster them into the different parameter. So you're kind of further stratifying them, right? And then you grab one of these guys, one of these guys, and one of these guys, and that represents your sample. Okay? Convenience sampling. These are obtained from individuals readily or conveniently available from the population to take part in the study. So these are people there that are ready to assist you. Now, you have to kind of take that with a grain of salt, because the people there that are trying, that are ready, willing, and able to be interviewed or counted or studied, right? Yes, they are important, but what about the other people who are not readily available, who are not willing to participate, who are not ready to be studied? their data is being lost, right? So yeah, you know what I mean? You got to take this there with a bit of grain of salt. When a sample is needed very quickly, boom, that's a good one. It is data, okay? When it is very difficult to collect a sample or introduce randomness to the selection process, when data obtained from a convenience sample are adequate for the study. So the sample may not be a representative sample, as I was just kind of alluding to, and therefore you cannot generalize the results obtained from it to the larger population. Okay, so this one here you got to take with a bit of a grain of salt. For example, in the diagram, the green population is being overrepresented. Okay, and the orange population is not being represented at all. Right? This is the researcher. These are the people there that have come forward. Convenience sampling should only be used when no other sampling method is feasible. Right? And yeah, you can make great data from this, but there's going to be a big asterisk beside your study saying that nobody from the orange dots was included in this. So we don't know what they're thinking. Okay? Identifying sampling methods. Yeah, this is a good one there you'll need for your first assignment. A survey is conducted by randomly selecting 5 health clinics and interviewing all employees working at each selected clinic, okay, to provide feedback on the working environment of clinics there in the region. What do you think we should do here? So a survey is conducted by randomly selecting 5 healthcare clinics and interviewing all employees working in each selected clinic to provide feedback on the working environments of the clinic in the region, right? A dietitian explores the relationship between the fat percentage in a patient's diet and coronary heart disease. To obtain data for this study, the dietitian solicits volunteers from the client and her practice. Which one of these ones would be that? That mouse is too sensitive. And a pharmaceutical company estimates the mean dollar revenue per sale during the past month. It finds that 200 sales invoices were recorded and decided to select 10 invoices only to do the estimate by selecting every 20th invoice starting with the 7th. That one sounds a little familiar. Sampling errors are the differences between sample statistics and their corresponding population parameters. Sampling errors are not mistakes. A way to reduce sampling error is to increase the sample size. Now, you remember, we were talking about that if you're going to take a sample, 20 people, and project it against the entire population of Canada, you know, what's that, 30 million, 35 million people? Are you really, you're going to take 20 people and project it onto the entire 35 million? Yeah, good luck with that. You're going to have some error, right? Now, whether it's 1% error, 5% error, 10% error, you know, and you're never ever going to get away from this. So sampling error, and as the PowerPoint correctly states, it is not a mistake, okay? It's just a fact of doing statistics. And the only way to reduce that sampling error is to increase the sample size. So the example I just said there, 20 people projected onto 35 million. Well, okay, if I do 100 people, okay, that's more people there that I've interviewed, and I have more data that is behind me, so I can make a statement upon the entire population. But is it going to be 100% true? Probably not. If I did 1,000 people, oh, I got more data. Okay, I have a better understanding. If I interviewed a million people, well, okay, now you're getting into you're getting into numbers there that are actually kind of close to the population itself. But the bigger the sample size, the less error you should have. Sampling errors are unavoidable even if the sample is properly selected and the data is correctly processed. You're never going to get away from it. Okay. Non-sampling errors include errors from data selection, calculations, and interpretations. Non-sampling errors include errors in the sampling plan, sample selection errors, data processing errors, calculation errors, result interpretation errors, research bias. Increasing the sample size does not alleviate the impact of these guys. Okay, these ones here should never be around. These ones here, the experimenter has control over. Okay, errors in the sampling plan. You know, instead of using a random sample, I should have used a stratified. Right? That's on the experimenter. Sampling selection errors. Again, the experimenter is in control. Data processing errors. You got to do the math right, right? Results, interpreting the results. Okay, this is all experimenter. This here you can reduce with good planning and good results. Okay. If a sample is not representative of the population it is obtained from, then it is biased. Okay, there's that word again. We never ever want to have any type of bias in our statistics. We want to let the data sing. We want to let the data speak for itself. Okay. Selection bias. Sample data is obtained using a selection method as not appropriate. Self-selection bias. Sample data is obtained from respondents who choose to include themselves in the study. You guys can see what's going on here. Non-response bias. Sample data is obtained from a survey with a very low response rate. Again, you can kind of see here how this information or lack of information, would affect your results. Okay. More on the same topic there. Examples here. Small sample bias, where the sample data is obtained from a very small number of individuals in the population, right? You need to get some type of a picture. If you're going to project this data onto the entire population of Canada, you know what I mean? That sample, in some regards, has to represent the population of Canada. And you do need a certain number, okay, of individuals in your sample. Researcher bias. Sample data is influenced by the researcher using questions that are loaded or leading, right? Are you just asking a question for information, or are you leading the participant in a particular direction? Can't do that. Unverified response bias. Sample data is obtained without the researcher verifying the accuracy or validity of the response. Everything falls under the researcher. Okay, the researcher has to keep everything in order. The danger that these bias present is that the results obtained could be nonsensical. Okay, they could, and you look at this there, if you're talking about a heart drug, this is serious stuff, because people need this, people will use these drugs. And if you skew the data there and say that this heart drug is actually working, then people will use it. But what if this heart drug actually makes people sicker, right? More sick, right? So it's pretty serious, okay? Bad graphs and deceptive presentations here. Graphs are the easiest presentation, as we talked about there in chapter 1.1. As a result, they are often used to mislead or guide people to some predetermined conclusions, right? And just zooming in here, right? The percentage of international students, right? You can kind of see here from 2005 to 2014, it appears there the percentage of international students is going up. Okay, and you look at your your scheme here at the side here. It's jumping up by 2. So 2, 4, 6, 8, 10, 12. You look at that, and it's high, and I mean it's high on the graph, right? Like you know, and it looks like there it's a minimal jump, right? It's going from 8 up to 11. So over the course of 9, 10 years, the number of international students has increased by 3%, which isn't a huge amount. But you kind of look at this graph and you go, whoa, that's a pretty dangerous graph. Look at this one over here. It's this, you know, it's the same graph. And this one here even looks more dramatic, right? We've got students there from I guess 7.5. I guess that's around 7.5, sure. So 7.5. This is more accurate, right? Because I can actually, because we instead of jumping by 2s here, we're now jumping by a half point. So you can kind of see here now that this looks like an enormous jump, but really it only jumped 3%. And then we've got this graph over here. You look at the scale, it's 10, 20, 30, 40, and according to this, it looks like the number of international students hasn't really increased at all. So you have to, when you're making your graphs, you have to make the graph representative of the data itself, okay? Or it could be misleading or guide people there to some other predetermined conclusion, okay? Yeah, you just have a look here there. The first graph is the fair representation of it, okay? And it has increased, okay? And it demonstrates there that it's increased slightly, okay? Which it has been. These international students have increased there from 7.5 up to around 11. So it's about, you know, 3.5%. Okay, if anything, I would have the graph in and around here. Okay, but what do I know? The second graph shows what we call a truncated y-axis starting at 7% instead of 0, and you can see the effects on that. Okay, third graph here shows an extended range there along the y-axis. Because the different scales used on the vertical axis, the graphs are visually quite different. So the scales you use are very, very important. Okay. If there is a relationship correlation between the two variables, now what do I mean by that? Where one causes the other. That's what a correlation means. Okay? Like eating McDonald's food. Is that the reason why somebody is put on weight, or is the reason why they put on weight is because of stress, or is the reason there they put on weight is because of genetic issues? Yeah, it's easy to, to say there that one causes this, one causes something else, but you got to be careful, right? You remember there from chapter 1.1 we introduced there confounding variables. Those are the issues there that an experimenter has to remove. Because if you're really going to come up and say there that this person put on weight, or this group of people put on weight because they eat too much McDonald's food. Okay, it sounds logical, but are there any other possible variables there that the experimenter missed? Could these individuals have put on weight because of stress? Anyway. So, if there is a relationship, a correlation between the two variables, it's sometimes incorrectly interpreted there that one caused the other. Causation, which is not necessarily true. Correlation does not necessarily equal causation. There could be a correlation, could be positive, could be negative, but you have to be careful there. Correlation does not equal causation. So consider these two variables there. Number of immigrants in Canada over the last 15 years. Number of same-sex couples in Canada over the last 15 years. Each of these two variables have been increasing in value over the time period, so there is a strong correlation. It is, however, incorrect to say that one caused the other. Obviously, right? Okay. With percentages, it is always important to examine the actual value, okay, in question, right? Hiring a new professor resulted in a 200% increase in the number of failing students. It is possible that the number of failing students increased from 1 to 3 after hiring a new professor. So out of 500 students, while an increase in the number of failing students from 1 to 3 does not sound alarming, an increase by 200% certainly does. Percentages are often misunderstood and definitely misrepresented and used for manipulation. And that's one of the things there with statistics. Depending, you can, you could say there that 50% of the population voted for this guy in the election. And you're thinking, wow, this guy got 50% of the vote. That's ridiculous, man. Wow, there's so many people voted for this guy. But then you can flip the whole thing around and say 50% of the population didn't vote for this guy. Both statements are true, right? But, and that's kind of statistics there, is that once the data is out, it's up to the experimenter there to present the data in the way there that they want to, okay? And it can be misunderstood and misrepresented for sure. Percentage points, okay, or percent points there are used to describe the arithmetic difference of two percentages. So an example here, an investment that previously returned 2% now returns 5%. The return on investment has increased by 5 minus 2 is 3 percentage points, but percentage change is not 3%. How so? Because the original, okay, was 2. In this case here, percent change, and this little formula right here, percent change is equal to, it's very similar there to calculating error. New value minus original value divided by original value times 100. And you'll see there that the percent change, 5 minus 2, which is 3, divided by 2, and you'll see there that the percent change is actually 150. Okay, because 2% is 100. That's 100% of what the original, and then the percentage increased by 3. Well, 3 is 150% of 2, and that's where they get that number from. Hopefully that helps you guys. We're going to be moving on there to chapters 2.1. If you have any questions, reach out to me, ian.coates@georgiancollege.ca. Take care. Have a great day.